Welcome in the second video devoted to rotation. This course is based on chapter 10 and 11 of Fundamentals of Physics from Wiley. We'll study here torques and angular momentum. So first we will define the torque and then introduce the work done by a torque, the power, and the work kinetic energy theorem. In the second part we will introduce the angular momentum, L, also the Newton's second law in angular form. We'll discuss systems, conservation of angular momentum, and rigid bodies will be done in the future lecture, not in this lecture. So if you search internet for the word torque, you will actually find this as your first choice. At least it's what I find. So first of all, it shows that science is not very popular on the internet, but you can still find some information here. Torque is in fact a quantity that is used in engineering, and it is related to engines and the efficiency of producing rotation by engines in motorcycles or in cars. Okay, but of course it's not our objective here. So staying with cars, you know that when you want to change your wheel, for example, you use this kind of tool, and you prefer using in general this tool rather than what is given with the car, usually a small tool. So this one has a very long arm here, and this allows you to easily unscrew the bolts here. So why is it easier with a long arm here? Let's find out. So how can we produce rotation efficiently using a force? So let's take the example of a door. You have the door is here, and you have the hinge here. So the axis of rotation is here. So we have three forces here. F1 is applied to the end of the door here, but it is on the line going through the hinge, through the axis of rotation. F2 goes directly on the axis of rotation, and this 3 is applied to the end of the door like F1, but with an angle compared to this line. So it makes it common sense that F1 and F2 will not produce rotation, because in fact their direction, their line intersect the axis of rotation. So what is important is that you must have the force must be applied farther from the axis, far from the axis. Okay, the line should not cross the axis. So distance from the axis is an important factor. You know that also here F3 is applied far from the axis, but if you apply, let's say, a parallel force very close, you will find out that it is more difficult to close the door. So distance R is important factor. Of course, it makes sense that the greater the force, the easier it gets to put this door in rotation, so the magnitude of F is also important. Okay, so this condition is from the fact that in F1 and F2, the F1 does not produce any rotation, even though it is applied very far from the axis, and it can be as strong as you want. So the angle with respect to the arm is also important. Okay, here his angle is 0, and you have no rotation. Here it is close to 90 degrees, you have efficient rotation. F can be decomposed into two components, so ft orthogonal components, ft and fr. So you see that ft is perpendicular to r. Okay, so only this tangential force will in fact be efficient at producing rotation. So we must define a new quantity that describes the effectiveness of an interaction at producing rotation about a specified axis. So this is called the torque. Torque is defined as a vector, so it has a magnitude, which is a distance from the axis of rotation multiplied by the tangential component of the force. Another way to write it is the magnitude of the force multiplied by what we call the moment of arm of F. It's also called lever arm. Okay, so we will see in next slide what it is exactly. The vector has also a direction, and this direction is related to the direction of rotation. So remember, we defined omega as a vector in our previous lecture, and the sign was depending on whether the rotation was clockwise or counterclockwise. So it will be the same for the direction of the torque. Okay, so let's discuss first the magnitude of the torque. So we have seen that it is defined as the distance of point P from the axis, so this is r, multiplied by the tangential force. So defining phi as the angle here between this line that supports r with F, we see that Ft is in fact F sine phi. So this is the first way to calculate this torque. It's also written here. So it is Ft is F sine phi. Now look at this drawing. We extend the line acting on line of action of F here, and we take the distance of that line with the axis of rotation. So this distance is r perpendicular because it's perpendicular to this line. This distance is perpendicular to this line, and this is called the moment of arm of F. So you have a new way to calculate F. Of course, it gives the same result. The final result is r sine phi F. But now, instead of putting the sine phi to associate sine phi to F, which gives Ft, you assign sine phi to r, which gives you r perpendicular. Indeed, r, so phi is also here, of course. Therefore, this distance is r sine phi. Okay, so you have two ways of calculating your torque in practice. Which one you choose will depend on the situation. Sometimes it's easier to find the lever of arm than to calculate this, so it will depend on the situation. Okay, so the torque is a vector. So what kind of vector is it? Let's look at the magnitude of the torque. So it's r F sine phi. This should trigger something in your brain, because you have here already written in black, r is a vector, can be considered a vector from O to P. F, the force is a vector, it's in blue here. So Rf is in fact the magnitude of vector r multiplied by the magnitude of vector F, and then we just have sine phi. So there is something in mathematics that will give you this sign, and it is the cross product. of r with f. Okay. If you calculate this, the magnitude of this vector, it will be of course the magnitude of r, the magnitude of f, and the sign between the two vectors. Going from r to f. This is important, we will come back to that. Okay, so phi is between vector r to vector f. Okay, so just you have to be careful when you calculate a cross product. When you choose your system, your axis systems, you have an x, y, z, an x, y, and z space reference. So you must choose your z such that it is x cross product with y. So these are unit vectors. Okay, so don't put the positive z downwards, even if it is convenient for you. You have to respect these rules if you want your cross product to give the right sign. Okay. So what about the direction of tau? Okay, so it's a cross product, so it's given by the right hand rule. Okay, another way is that I use sometimes is a rule based on the screw. So I have already introduced this rule for finding the direction of omega, the angular velocity. So it also works to understand where the tau should point. And in fact, this rule can be used even if you don't use the cross product. Okay, if you just deal with magnitudes and you don't really want to calculate a cross product, but you still need to know where the torque will point at, and so you can use this screw rule in this case. So what it does is that again you imagine a screw positioned at your axis of rotation, and you look at what kind of rotation will be induced by f. So in this case, f tends to induce a rotation in this way, okay, which is a view from above, a counterclockwise rotation. So if you have your screw, of course you look from here, and counterclockwise, it means that your screw will move backwards. Backwards in this system means a view from above along positive z. Okay, so your torque will be along positive z. Okay, so it works. Okay, so the torque is here. Okay, let's go back. Let's discuss a bit more the sign of a torque. So again, if you don't calculate the cross product, you will have to find out the sign of the torque in order to solve the equations. So basically, if the torque tends to produce a counterclockwise rotation, it is positive. So this is looking at the xy plane from above. Okay, so if it's moving this way, it's positive, which indeed is along positive x z. Otherwise, it is negative. So this is the convention. So you can decide a positive direction like this. You could decide another that the positive direction is clockwise, but then you have it to be consistent across all your calculations. Okay, and this, if you decide this, you don't use cross products. Otherwise, you will have some problems. Okay, or you have to choose again that z equal x cross product with y. Okay, so if you have a nice system of axes x, y, z, then you can calculate your tau using R cross product with F, and the sign of tau is given by the direction of the axis. Okay, because the tau will be along that axis, so you will have the sign automatically coming from the calculation of this. But if you don't want to use this cross product, you calculate tau in this way, so you have magnitude of R, magnitude of F, and the sign, and then how to know you have the proper sign or not, the proper sign. So it turns out that you can calculate it this way, and the sign of tau is in fact in the sign phi. Okay, so you have to be very careful in selecting your phi. Do not mistake. So phi is taken from R to F. So if you so F is here, so you can draw again your R vector from this point, so it would be here. So from R to F you go this way. Okay, R to F, and this is a counterclockwise angle. It's a positive according to our convention, and this will give you the proper sign of the tau component on the z-axis. Okay, so we have defined the torque, so now let's do what kind of work can be done by a torque. We limit ourselves here only to pure rotation. So let's consider a point here. So the axis of rotation is here. It is experiencing a circular motion. And there is a force F applied to that point. So the element of work, as you know, is F scalar product with the displacement, which is here delta S. So you calculate this scalar product, so it is F delta S and the cosine between F and delta S, which is cosine theta. Okay, so we have to estimate delta S. It is R distance multiplied by delta theta, so we can replace this in the equation. R cos theta, F delta theta. So you realize that R cos, so R is here, cos theta is this length. Let's call it R perpendicular. So we get R perpendicular F, and this is by definition the magnitude of the torque. Okay, lever of arm multiplied by the magnitude of F. This is the torque. So it's tau delta theta. So we take the limit when delta theta approaches 0, and we have our elementary work. So the total work from an initial angle to a final angle is just the integral of this tau d theta. Okay, for the particular case when tau is a constant, of course tau can be taken out of the integral, and you just have your work equal to tau and then the difference in the angles. You can also get the power. So the power will be by definition dw dt, and in such a case you have, so dw dt, you have tau d theta dt, which is omega. Okay, so let's continue with the work and energy. So we have, you know that you have a work kinetic energy theorem in linear motion. We have the same thing in pure rotation. So the difference, if you have two states, the kinetic energy in the final state minus the kinetic energy in the initial state will be equal to the change in kinetic energy of rotation. And yes, I mean it will be written in this way. So with omega f for final and omega I for initial, and it will be equal to the work done by the net torque from initial state to final state. So when using conservation of energy in general, rotational kinetic energy should also be considered in your calculation. Let us now establish Newton's second law for pure rotation. So we have here a point, mass m, rotating, so it is in a horizontal plane, so that gravity is along the vertical line, going into the page, and there is a reaction going towards us. So there is an additional force, F, here, and it can be decomposed into a horizontal line and radial component. So let's apply Newton's second law for linear motion along the tangent line here. So we have Ft equal mat. So we are studying rotation, so it would be nice to have a torque showing up in this equation. So the torque is Rft, so let's multiply by R, we get this. Then we would like to get rid of this linear variable and replace it by an angular variable. So At is in fact R alpha. Doing so, we get mr squared alpha, and this is the moment of inertia about point C. So this is our second Newton's second law for pure rotation. Okay, so here we summarize pure rotation about a fixed axis and pure translation, fixed direction. So we have already seen in our lecture on rotation that there is a correspondence between the two, like x correspond to theta, v to omega, a to alpha, m, the inertia, correspond to I. Now we have seen also that F net equal ma is in fact equivalent to tau net equal I alpha. So F, now the force is replaced by the torque, m is still like the inertia is I, and a, the acceleration, is alpha. So these are the same equation in fact. The work is the force by displacement, so here we have a torque by an angle, so again the same, x is replaced by theta, okay, x by theta. Kinetic energy half mv squared, so half of inertia speed squared, same thing for rotation, and same thing for power, force speed, torque speed. And we have also the work the work kinetic energy theorem in both cases. Okay, so let's now introduce the angular momentum for a single particle. So from linear motion we had the force, so we got in angular motion we got the torque, and the torque was built in this way. We had R cross product with F. In a linear motion we have the linear momentum P equal mv. So how do you think we can build an angular momentum? So from here to here we just applied a kind of operator, R cross product. So we do the same, R cross product P. This is our definition of angular momentum. So P equal mv, and m is a constant in classical mechanics. So we can take it out of the cross product and we have R cross V. So one thing to be careful about is that L and the torque actually both are related to a point. So both are defined about a point, which is the origin of R, vector R. Okay, so the magnitude, how to calculate this angular momentum. Okay, so it's just RMV sine phi because it's a cross product. So this is the magnitude. You can also calculate it by taking R and P perpendicular. P perpendicular, this one tangential, RMV perpendicular. You can also take R perpendicular, that is the level of arm, multiplied by P. Okay. Most of the time you will just take RMV sine phi. Okay, these are maybe some particular case. It may be simple for some reason, but okay, most of the time keep this way. So it is a cross product of R cross P, so obviously it will be this way in this case. Alright, so you can see. Alright, so here I would like just to show you another way to calculate the angular momentum in the case of pure rotation of a single particle. So we have seen that it is RMV, but there is another way. Okay, let's see. So we have here a point M rotating. So there is omega like this. So this is our angular momentum. So it's RMV along UZ. This is a unit vector. Okay, but what if we replace V, which is a linear variable, by an angular variable? So V equal our omega. We replace this, we get L0 equal mr squared omega. So omega is a vector pointing in the right direction, so that's perfect. And mr squared is in fact the moment of inertia of this mass here with respect to the axis of rotation. So we can write in fact L0 equal I0 omega. So that's another way to write L in this case. And for a rigid body, we'll see that most of the time we use this formula. So there are two ways of dealing with circular motion of a single particle. So it depends on what you get in the problem. If they give you the mass, this is better. If they give you I0, or for some reason you may have a system or something, so this may be better depending on the situation. Okay, so now let's see the second Newton's second law in angular form for a single particle and for the general case. Remember, before we have just established the Newton's law in angular form for circular motion. This is for in the general form. So we have L given in this way, so we would like to know how it changes with time. So we take the derivative. So derivative of a cross product, it follows the same rule as when you take the derivative of the product of two functions. So if you have, let's say, u, a product of function u with function v, you will have, so the derivative of uv will be derivative of u multiplied by v plus u derivative of v. So the same thing is done here. We have R doesn't change, we have dv dt plus dr dt v. Okay, with cross product everything. Okay, so dr dt is v and dv dt is a acceleration. We get this. So what about the v cross v? Well, if you calculate the magnitude of that, you have a v squared sine 0, and sine 0 is 0, so this term is 0. Alright, a we can also express it as together with m we have f equal ma, so this becomes r cross product with f net. Alright, so f net it is the sum of the forces, so you can write it also like that, the sum of all the forces. Okay, so in the end, this is what we have established, the Newton's second law in angular form, and this is a general thing, general law, always valid. So again, be careful, this is taken about point, a given point O, and this one also, same point O. Alright, let's see a system of particles. So it is quite easy. The total angular momentum is the sum of all the angular momenta of individual particles, so it can be written like this. So you take the derivative, so you have the sum of the derivatives and the sum of the net torques. So we have in fact the same equation for a system of particles. So about this formula, so far we have always seen that there was a correspondence between linear motion and angular motion. So what is the corresponding equation in linear motion for this? Well, you know, torque in linear motion becomes F, the force, so F net. L is the momentum, so in linear motion you have F, so it's another way to write Newton's second law in linear motion. It is the force equal dp dt. Okay, so this is the same in angular form. Okay, so something very important. You have seen in linear motion that the linear momentum can be conserved, always. So, and so is angular momentum. So it's actually quite easy to see. If there is no torque, dl dt is 0, therefore L is constant as a vector, not only as a magnitude, but also as a vector. Okay, so L is constant. So this means this is very powerful, because if you have an isolated system which changes in some way, so it evolved from an initial state, here I, to a final state. So if the torque is 0, you know that these two are equal. So you can compute L in the initial state and L in the final state and solve for whatever you need to find. So now this is in the case for when the total torque is 0, so the total angular momentum is a constant, but you the torque the torque and the angular momentum, of course, can be have several components. In 3 dimensions you have 3 components, for example x, y, z. Therefore you have in fact this translates into 3 equations, right? One for x, one for y, one for z, using Cartesian coordinates. Alright? So in fact, if tau net along z is 0, then you have dl z dt equals 0 and lz equals constant. Even if ly or lx is not a constant, you have lz is a constant, and you can use this as well. And often this is very convenient. You don't need to have full conservation of momentum in your system. One component is enough to have an equation. You can get actually 3 equations with this formula. As you could have, in fact, in linear motion, you also have 3 equations from the vector equation. F equal ma, you can have 3 equations, one for x, one for y, and one for z. Okay, so here is the formula summary for this lecture about torque and angular momentum. We have seen the torque defined here, the work of the torque, the power, the work kinetic energy theorem for pure rotation, angular momentum was defined, Newton's second law, the general form is here. For pure rotation you can write it like this. Thank you for your attention, hope it helps.